your work. Okay?
Thank you.
Thanks.
So, I don't know if everyone can hear me. I think it's okay. So today I'm gonna present you my last work within uh, deep reinforcement learning. So mainly I use the robotic arm in order to deform a soft object using deep reinforcement learning. So I'm gonna start by make a brief introduction on the usage of this soft linear object and why they are useful within robotics. And then I'm gonna go to explain in a more specific way the problem statement and how it is solved within the state of the art and what are our contribution with respect to that, of course. And then I'm going to go to introduce, but in a really brief way, the framework we use to perform our experimentation. And I'm going to show some examples of them. And in the end, I'm going to conclude the presentation by explaining also what I'm planning to do as a future work. So about the introduction, as I was saying, those deformable objects are nowadays really, really important in robotic research, and more specifically, the deformable linear object called DLOs, because they have lots of application within automation, such as you can see here, cable harnessing, wire soldering, and plant manipulation in general. So about the statement of the problem statement, as you can see here, I'm having this robotic arm, which gonna deform this soft linear object. And for making it a bit easier, I fixed one side of the bar and the other side is already grasped by the robot in order to not have to deal with the grasping part. So, and this object is actually described using a mesh. So I model it using a tetrahedral mesh. And for describing the deformation, I selected a set of those mesh nodes. And the objective is to move those selected mesh nodes, the blue one in the screen, and to deform them such as they reach the desired position, which are the red crosses, okay? And of course, that kind of problem is complex because when you don't have a really good deformation model of your object, it's hard to do the indirect control by just controlling the gripper and not having any mechanical information about the deformation model of the object. So in the state of the art, one of the proposed solution is first, the most obvious one is to have this mechanical deformation model and to use it to do some dynamical planning, like manipulation planning, in which you, I think someone gonna join the teams, I don't know. Okay, okay, I don't have to deal with that. Okay, sorry. So I was saying that when we have this model, we can do some manipulation model, like some manipulation planning based on this model. But this model is hard to get. So we prefer to do an online control and without having no knowledge about that mechanical model and just try to deal with inverse control. So this was also done in the state of the art. So some research was focused on such scenarios, but most of them were addressed for 2D workspace. So as you can see here, the deformation is in the 2D plan. Like this is the initial shape, the A, and this is the final shape, the D. So both are in the same plan. And the one which considered the 3D workspace consider really small deformation with really small object. As you can see there, the object in gray, it's like this is the initial position. I don't know if I should take the mic. Like this is the initial position and this is the final one. So the difference between both is really small and the same for another object. So because of all of these challenges, we prefer to use a solution based on DRL. So for DRL, the solution given was addressed for really easy and simple problems, either for DLO or not. So as you can see here, for example, this is a piece of cloth, and the goal is to put it on the hanger. So as you can see, each time it's actually the same scenario, like they start from the same initial configuration and end up with the final desired configuration. And the same for DLOs. So there is a rope, and the idea is to bend the rope and unbend it, but still following a special configuration scenario on which we move from T0 to T1, and then from from T1 to T2, etc., until the end and going back. So, and the second problem is those objects were modeled using a 2D mesh, not a 3D, which is like made of triangles, not tetrahedral. So the main drawback, as I showed of this technique, is that it is not easily generalizable, their framework, since they usually start from some same initial configuration and end up with some same initial deformation. And this was used in the training and in the testing phase, so we cannot really deal with other configuration. And this is, let's say, one of my main contribution, is that within my framework, the robot is able to deform this DLO by starting from different configuration and ending up with different configuration. Of course, the training is performed for the same specific object, like we cannot change the object yet. This is done because mainly I'm using different deformation boxes. So as you can see in the figure, the blue box is a box within which the arm can move. So this is the workspace of the robot. And then we have two red boxes. Both of them are used in order to make the gripper moves within the box, randomly or sequentially, it doesn't really matter. And when the robot gonna move, the object gonna be deformed differently. And we record those deformation in order to keep them in memory, as then select them as desired deformation to achieve. So in the training, we use the small box to do that. And for the testing phase, we use the bigger one in order to be sure to have new deformation that the robot wasn't trained on. So the second contribution is that the object I use is modeled by a 3D tetrahedral mesh. And that, of course, I'm doing some deformation in 3D. And as you can see, it can involve some complex torsion. So for my framework, I use the classical RL procedure within which we have an agent, so the robot, which is in a specific state, like so the object has already a current position. And then the agent gonna take an action, which simply means that it gonna goes to the gripper gonna goes to another XYZ position. And as a reaction to that, the object gonna deform differently. So we're gonna have a new current position. And how can I do that? I go out. This one? Something like this? No? Oh. This? So this is okay? Yes. Okay. So I was saying that I'm using a classical RL procedure within which the object starts from a certain state, so certain current position, and then the agent, the robot, gonna do an action, which is simply move the gripper to a new XYZ 3D position. So as a reaction to that, the object gonna move, the position of the selected mesh nodes gonna move. And so we're gonna go to the next state, and etc., etc. And of course, the goal is that those new current position mesh reaches the desired one. So the policy behind the agent is looking for is to try to optimize the reward over the different steps to be able to link for a given state, being able to say, okay, which action should be performed in order to make the object reach those desired positions. So we use for that, of course, the Bellman equation. So mainly the Bellman equation for training the agent, we use the Bellman equation. So this Bellman equation is simply used to attribute some Q values, so some kind of evaluation to the state action pair. So for that, of course, we're going to use the reward, which is already an evaluation by itself, but we're going to add to that a second term, which is the next Q value. So mainly that how much we care about the next rewards that the agent going to give in next steps. So we use also this discounted factor, the gamma, in order to weight how much we care about that future. So I use DDPG, Deep Deterministic Policy Gradient Actor-Critic algorithm. So it's mainly a DRL algorithm within which we have two networks, the actor and the critic. So the actor gonna learn the policy, like gonna give some actions given a certain specific state, and the role of the actor is gonna criticize the action given by the actor by attributing to it some Q values in order to evaluate how well the actor performed. So here, as we can see, simply as a pre-procedure training, let's say, I didn't mention it, we're going to make the robot move within the box in order to record the state, the action, the next state, and the rewards. And we're going to put all of them in some memory that we're going to call a replay buffer. And for training, we're going to extract some batches, so some, let's say, sets of state, action, reward, and next reward, in order to train over those batches, no longer on one state, one action, etc. So when we do that for the critic gonna simply, for the state and the action, gonna give an evaluation, which is the Q value. But the ideal is to have the same value as the Q value of the Bellman equation. So simply the training consists of minimizing the difference between both, the Q value given by the critic and the Q value evaluated by the Bellman equation. So since in the Bellman equation, I put it back there, we have this Q next value, which we don't have now. So we use the critic in order to have this value. So we give to the critic the next state and the next action, and we take the Q value given by the critic and we use them within the equation. For the actor, in the other side, it's just the loss of the actor is based on the Q value evaluated by the critic. So it just like we are trying to either maximize the Q value, but in our case, we try to minimize the negative value of the Q value in order to minimize a loss. It was more logical, let's say. So, and about the reward, we calculated them as average Euclidean distance over all the selected mesh nodes over the soft object. And we add also another, let's say, principle, which is learning parallelization. That principle was applied originally to another actor-critic DRL algorithm called A3C. So mainly, for doing that, we have to execute multiple agents in parallel on different instances of the environment asynchronously. And this, by combining these to batch extraction, it's actually going to decorrelate the training data and going to collect them faster, which going to lead simply to have less overall learning time. And also the agent going to be able to generalize much easier after, because it learns from different experience at the same time. So about the experimentation, we conducted 3 training for controlling 2, 4, and 3 mesh nodes. We used 32 agents trained in parallel. So each one of them performed 63 episodes. So if you do the multiplication, it's going to lead to having in the end 2016 episodes. Each of those episodes was made of 300 steps, which means that the robot can perform 300 actions in order to reach the goal. So we use also an average distance error of 5 centimeters. This means that if on average the distance is far away from the goal of 5 centimeters, we consider it as achieved. And yeah, we use so the small database, as I mentioned previously, to make the training, and we reset the environment after each episode. Reset the environment means that the object and the robot goes back to their initial state, which were this vertical state I showed in the beginning. So as we can see here about the learning curves, on the contrary of other curves in the literature, I didn't have to smooth them because they are already smooth, as you can see, since this learning parallelization allow to have a really stable learning. So for the testing, on the contrary, I made an average over 1,000 tests. Each of those testing episode was made of only 30 steps. And I tested using the average distance error on 3 centimeter to be more precise, and the 5 centimeter as in the training. Then I tested on both database, the small and the large one. And in the end, I test them by reinitializing and without reinitializing the environment. In case that we don't reinitialize the environment, simply the last deformation in the previous episode gonna be the initial deformation of the following episode. So here I'm gonna show you some examples. So I think I can up. Here in the beginning, I just controlled 6 mesh nodes on the large database and without reinitializing the environment, and I keep the precision as it is over 5 centimeter. So up. So as you can see, the robot start from this vertical position, which is the initial one, and try to bend in order to make those points reach the desired one. And then after it's done, it's gonna go back to its initial position and start over again. So the second test is for controlling this time 4 mesh nodes, still on the large database and still by using 5 centimeter as the threshold, but without reinitializing this time. So as you can see, the object bends in order to reach like the desired deformation, and then it's gonna start from this deformation in order to achieve the following one, etc., etc. So here again, it's trying to like stabilize it, and then it's gonna go for a third one. The last test is for controlling 2 mesh nodes on the small database, but this time by being more precise and having an average distance error of 3 centimeter. And I didn't reinitialize, I reinitialized the environment in order to keep one change on time. So here, as you can see, it's a bit harder to achieve because it requests more precision. So it's gonna oscillate a bit and then stabilize and do it. So let's say that the results of those 3 tests is that in the first one, the robot was able to achieve almost 79% of the deformation. For the second one, about 73% of the deformation, and the last one, 80%. So as a conclusion, what I can say is that our framework prove its generalizability since we train using some conditions which are being precise around 5 centimeter, extracting the deformation from the small database, and then use a reset after each episode in order to reinitialize the environment. But while testing, the agent can be more precise. It can perform some deformation for which it wasn't trained, and it can even deal with the environment if it is not reinitialized. So there is, however, some limitation, of course, is that we cannot combine those changes together. Sometimes it works well and sometimes it works badly. So as an example of when it works well is the second test I show you for the 4 mesh node. I changed two things since I used the large deformation and I didn't reinitialize the environment. So here it was performing well. Like, as I said previously, it was about 73%. It could achieve 73% of the deformation, but some other time it doesn't perform well at all. Like, for example, in this third test, I use a small database, like the one I show you. But if I use a large database this time, it gonna perform only 21%. So when we increase the precision, it's kind of difficult to add to that other deformation than the one the agent was trained on. So this work was accepted for publication in the proceedings of IEEE case 2022. And as a future work, the idea is to transfer this work to be able to test it in real. So I conducted some, let's say, preliminary tests. It's not really concluded yet, but what I could achieve is to be able to do it in real for the deformation on the above of the box, which means like more on XY plan than on the Z plan, because on the Z axis, actually, I discovered that the object, the real object, gonna try to bend naturally to one side, which is not necessarily the same side than the one, the bending one on the simulator. So of course, what the agent was trained on doesn't really, it's not really similar to what it was tested on. So of course, it's harder. So let me show you some of this example. Here it's when we are on this XY plan and with less Z. So here you cannot really, I'm not sure that it's easy to see, but this green is the desired one and those green are the current one moving here. So as you can see here, it kind of achieved, both greens are putting one over the other, so it's okay. On the other side, I'm gonna go out. So here is the real one. When it is on dead axis, as you can see, it bends on the Z, but I'm gonna show you another video. No. This one is RV's one, so it's easier to, cannot show it. Okay. I don't know even how to close it. Yeah, it's working well. So the green here points are the initial ones, so from where it starts. The blue ones are the current one, moving like the other video with the white foam bar. And those greens here are the desired one to achieve. And as you can see here, the object bends to the front and it should bend to the left. So because of that, the agent is gonna, like, it doesn't know what to do. It tries to goes above in order to have the foam bar straight again. But once it goes on that, it moves to the front and not to the left. So it's gonna stuck in this circle, let's say. For other deformation, however, it's easier. Like this one is bending to the right, but to the right front. It should be more to the right back, not like this. So as you can see here, the precision is around 11 centimeter. Like, I mean, the difference. So when it is not too much on that, it achieve it easily. So it's almost over it. But the problem is when there is this Z axis. So up, don't know how to this. Yep. Yeah, that's it. Thank you for watching.
Okay, thank you, Mélodie. Quite interesting presentation and nice to and easy to follow, at least the main points. Okay, is anybody here to make a question or comment? Yes?
Well, first of all, thank you, Mélodie, for this.
Maybe you have to
come here once.
Yes, if not.
what I was saying. I think you explained everything very well, very clear. I had a couple of questions regarding the moving from the virtual experiments to the real ones. So I guess you because the physical properties of the objects vary a lot, so you cannot reuse the learned model from the virtual experiments to the real ones, I guess, right?
Yeah.
Is it possible to try to adapt or transfer something that you have previously learned in the virtual world to the real one, or do you think it's easier to start to reuse the knowledge from the real from the virtual?
Like you use the trained model from the virtual, and then you're gonna train it again on the real model. This is a good idea, but however, it's not really practical. Why? Because originally, if we use simulator in order to do the training, is for some reason. First one is for not tiring the robot, because this training gonna take, I don't know, several hours, so it's kind of difficult to use that. But even if I tried it, but because of, you know, these markers, like you can see on the object here, which you're gonna detect.
Yeah, that was my second question, actually.
It's when you're gonna bend it, you have the cameras, it is not usually gonna see all the picture, because some of the, like the deformation over this white bar you see here, it's bending and it's hiding the marker, it gives some shadow. So it's not, sometimes you lose this detection, and when you lose it in the middle of the training, everything goes bad because you cannot continue training any longer. So it's not really practical to do that.
And would it be possible to train in the real world with different types of objects, I mean with different properties at the same time, in order to generalize to move different materials, I guess? Or
you can do it, but the thing again, once again, is that the difference between both materials, since they are foam bars in any case, it's not that huge, if I'm not wrong. The problem is that this sort of foam bar, since they are thin and really long, it's more than 1 meter. It's when you leave it even on a desk, you're gonna see that it's gonna bend to one direction. And because of that, when you're gonna put it back, even if you use the same material, same length, same everything, it's not gonna bend in the, as I was saying, in the same direction. And for now on, I don't know how to model that on the simulator. It's quite hard. So I'm trying to find the solution in order to maybe model this behavior in the simulator in order to be, as you were saying, able to train on different deformation models, let's say. But for now on, I don't know yet how to do that.
Okay, very interesting. Thank you.
You're welcome. I think now I think we can turn it on if you.
Thank you so much for the talk. I have quite a general question about how do you quantify or qualify the properties of the soft objects? Because all soft objects can be very different from one another, and if you are to compare with other people's experiments doing similar things, how do you compare the properties of the different soft objects that you're looking at?
It depends. So you have two ways to do that. It's either when you buy the material, you have some of the mechanical properties, such as the Young modulus coefficient, Poisson coefficient. It's hard because I'm going to say it in French, sorry. So when you have these values, so you have some restricted value, but as far as I know, there is some sensors, I'm not sure even if we have them in the lab or not, that when you do the real test, that's a traction compression test, you can have these real values. But generally it's over some ranges, let's say, some intervals. So it's kind of similar, like you have, I don't know, like this sort of things, the Young modulus, it's around, let's say, 10 megapascal. It's around that average, and everything it's Like, I don't know, some people are gonna say 7.5, some other, but these small changes doesn't really change big things in the simulator. Like, I mean, the trained model, I use some Young modulus and Poisson coefficient, which is not really similar to, of course, those real form. Since there is also the factor of error when they produce them. And still on this XY plan, it was able to work well. So.
Okay. Okay, maybe we can chat, because my work is involving virtual soft objects, but they're very complex structures, and I don't know a way of like qualifying them. But maybe we can chat another time.
Okay. It would be my pleasure. Thank you.
I have a question. Hello.
Hello.
Yes.
Hey. I didn't understand. I had two questions. I didn't understand the case. You had one case where it was really bad. It was like 21% or something.
Yes.
Why? I didn't understand why. I didn't exactly understand why that case was so bad compared to the other training cases.
Like, because I mixed two, let's say, difference between the test and the training phase. When you just use one difference between both, it works well. It's able to generalize. But of course, when you change two things, it's quite more difficult to generalize, which is kind of obvious. And in this case, I ask for two things. I ask it to apply it for other deformation than the one it was trained on, but also achieve a higher precision. And of course, for being more precise, it's difficult. If you are asking why I didn't originally make the robot train with higher precision, it's actually, I tried it. I didn't mention it in the result, but I tried it. And when you do that, you are asking for the agent to be so precise that it cannot really converge over the solution, because you have a really large workspace. And for being that precise, it's quite difficult. Even if you train the agent longer. For now, I didn't really expert it in a more precise way, but I do some, let's say, tests just to know.
Okay, and also when you were able to achieve between 70 and 80% of the deformations, why did it fail for the other 20 or 30%? What's any idea how to improve that to get it to be better?
Like when it succeeds, I just change one of the condition. So when you change just one, it's usually between 70 and 80. That's why I think it's better. How to do better is like the colleague was asking before. I think it's how to be able to generalize more. So this, you have lots of different perspective. I cannot really tell now on which one is the one that should be applied. But of course, you can start originally by change the material, change maybe the model of the object, having a more realistic model. So because even in the simulation, I mean, when you slow down the simulator or in the calculation, or you make it do faster calculation, it won't gonna behave the same. So all of these small changes for neural network, it's really big, huge difference. We cannot really notice them, but it's true. So maybe by doing some like sort of, how can I say that, setting up the parameters in another way or training them on another thing, maybe we're going to be able to generalize more. And at that time, of course, we will be able to deal with more differences.
Okay. And then last thing is, you had this reference 13 in a few of your slides. But I didn't see the actual reference. What was the actual reference? Oh yeah, what was this here? Okay.
The presentation in the middle, I'm sorry for that.
Oh, okay, yeah. It appeared many places and I didn't see what it was.
It's actually the DDPG main original paper.
Okay.
If I'm not wrong.
Okay. Thank you.
You're welcome.
Thank you.
Thank you, Mélodie, for your work and your presentation. Actually, the applications of this research is limitless, from the medical field to the industries. And I wanted to ask one question. is for the real testing you did. How did you know that the pose of that deformable object is reachable, that it's valid, that the object can be deformed in that manner?
Oh, because of the box I like explained previously here. This kind of box, like the red ones, from which I extracted the deformation, actually I made sure of two things. First, that it's able to be reachable by the Reaper, and second, that the object can do really the deformation.
And that's based on the physics dynamic models of...
yeah, like you just test it. I didn't really do big experimentation about that, but I just move it and see that everything goes fine.
Okay, so you collected the data through real deformations. Okay, thank you.
You're welcome.
Another question? I have a question. I am physicist.
Maybe.
So my question is, if the parameters you measure to train, you consider some physical parameters, for example, the torsion or the pressure, or even some sensors the robot have to measure this kind of parameters, or not physical parameters, not only the shape of the object?
No, actually, because this robot I use, Panda one, doesn't have such sensors, so it's impossible to do them. I mean, with this robot at least, as it is. Of course, maybe we can add some sensors. I don't know. So it's hard to measure them online. What I made is actually those foam bars. I got them from a store, and I asked the lady, the seller, to ask the guy who made them what are these parameters, and they give us some intervals, so I use them.
Yes. Okay. Well, I was saying more when you train, I think that you measure the position of the meshes and so on.
Exactly.
And among these parameters, maybe some physical parameter like the pressure, for example, the object does on the floor or something like that. Maybe these kind of parameters would give more information about the state of the object, because you measure the state, and after, with this state, you do the DLR process and so on.
Oh, I got it. What you mean is that I use this parameter to describe my deformation. So
Yes.
maybe with this extra information,
Yes.
Okay, I got it. I haven't tried. I need to.
Yes, maybe despite the robot doesn't have this kind of sensors.
Yeah.
You have, for example, only for testing, to put a small device between the object and the floor to measure the force, for example, and maybe this information can give you or the process for training more information to avoid this to say before the object bends randomly.
Yes.
So maybe this kind of parameters helps you to I don't know, to limit the variability of the parameters. I don't know.
Got it. I need to maybe read and search more about and see if it's possible to test. And yeah, good idea. Thank you.
No, well, and I have another. How much time the simulations you did in parallel?
Yes.
But
the overall time, you mean,
yes,
of learning?
more or less.
For that, like for that paper with that experiment, it was like the maximum one, because we made 3 training. it was about 3 hours and a half.
Okay.
It's not that long compared to real, like the main DRL training with one agent, it's more 8 hours or something like that. So it's long. But if we wanna, this is what I tried with one of my colleagues, like my co-author, to do is to slow down the simulator in order to have higher precision over the deformation. And this time, no, even if you do this 32, it can goes like for 1 day training or something like this.
Okay. Okay. Any other?
Well, I don't know if this is even possible in your specific context or your learning framework or for these robots, but have you thought in order to narrow the learning, let's say the learning input space for those difficult situations where the robot has more trouble, have you thought about using, for instance, some kind of learning from demonstration so that the user can give some feedback or some demonstrations to the robot, like moving it directly or something like that to show how to properly achieve that position?
This actually is like, let's say, the most used way in the state of the art, but I didn't try it because I was trying to find this contribution thing, so it's kind of difficult to have it, but maybe I can, I don't know, mix it and see if it is better for some specific deformation and not for all of them. But mainly what you can see in the state of the art, even if despite they say it's pure DRL, it's not really pure DRL. It's usually mixed with some human deformation. Yeah.
Okay, so your goal is just
My goal was just to use DRL, pure DRL, let's say, but maybe what I can do is instead of doing like them using demonstration plus DRL all the time, use deformation just for some of them, not all of them. Maybe I can try to need to expert and like, I mean, do some experiment. Of course it takes time.
I have along those lines, I have another, I guess, a question, which is, you show these videos of the robot bending the foam. If you tried it, are you able to achieve the task?
Yeah, in the, like, as I said in my first video, this one, the deformation was more on XY plans than on Z, because as you, I can bench it again, as you can see, the deformation here, it's a bit small on that, but more on XY, it's like a kind of really, let's say, soft S letter. So this I can achieve them, no problem at all. Like, but the problem is when I want to do this sort of deformation, which you have like really strong deformation on Z and with squeezing the robot. In this case, as I was going back to the video, here sorry, it's hard to be on both sides at the same time. Here, the idea is to go there. So this blue point should reach that green point. See, it's really, let's say, strong deformation on the Z-axis. And in this case, as I was showing in the reality, as you can see here, the object is bending to the front and it should bend to the rear left if I'm the robot. So it's not the same. And here, for example, it was bending to the right, yes, but here, right front, and it should be right back.
Yeah,
so,
I guess what I'm asking is, if you actually just took the foam in your hand and you had that task to do, are you able to achieve it? Can you do the alignment?
If I'm human,
not
yes,
even thinking about the robot right now. I'm just, if I give you a piece of foam and say, move it so that it's deformed like this, is it possible for you as a human to do it?
Yeah, for a human, it's easy because when you are on the above and you try to do it yourself, you have, let's say, more degree of freedom in your, I don't know how we call it in English, like this part wrist. Okay, sorry. So in your wrist, you have more degree of freedom. What you like the robot is doing, I don't know if you see my hand or not, is you press like this more, but you don't have this mobility. And when you are holding the foam like the robot, you're gonna do maybe a small way like this, or you're gonna bend it on the other side in order to make the foam deform as you want.
So
It's easier when you use both hands. So this
Right.
was one of the idea we thought of with one of my colleagues, is to have a dual arm to make it easier. Because when you grasp the foam from your both hand, it's much easier to do it as a human. But despite that, you can still do it. You're gonna maybe take more time, but you can do it. Yes.
Okay. So is the problem then that the robot doesn't have enough degrees of freedom?
It has the maximum, but the degree of freedom of a robotic arm, it's cumulative. It means that one joint has just 1 degree of freedom, and then you have lots of joints, so you have lots of degree of freedom. That one, it's 6 degree of freedom, 7. 7, it's because there is one which is like quite, we say mimic, it's like duplicated twice, so it's how can I say it? Redundant, exactly. It's redundant, so you don't really consider it, let's say, kinda for doing the motion. But as a human, in each one of your joint, you have 3 degree of freedom. You don't have just one. So with even just one articulation, you can do much more things than a robot can do.
Mm-hmm.
Because human body, it's like, let's say, superior to robots, of course.
Mm-hmm. Okay. Okay.
Exactly.
Robots don't have this feedback.
Exactly.
Before.
Yeah. This is the idea, maybe.
Yes.
Yeah.
Okay. Other question or comment? In Teams, there is anybody who want to ask? Anybody? No. Well, thanks you again for the presentation and the answer of the interesting questions.
Thank you for your advice. I'm gonna see how can I manage to. Thank you.
Yes.
Yes, everything.
I think I have